All right. Thank you for joining us today for DataBytes. My name is Amanda Miller, and I'm the Associate Director for the National Consortium for Data Science, or NCDS, which is a project of the Renaissance Computing Institute at the University of North Carolina, Chapel Hill. Today, we are thrilled to host Apostol Vassilev, an AI and cybersecurity expert at the National Institute of Standards and Technology, also known as NIST. Before we begin, I'm just going to share a few housekeeping items. We do have this webinar lasting through 1:30. We are recording the event and do plan to send out the recording for those of you who are unable to stay for the full amount of time. We have disabled Zoom Q&A for attendees, and chat is also disabled to really allow our speaker to present without distractions. But we do offer a place for you to share your comments and questions. You can post those to Easy Retro, which is our crowdsourcing Q&A platform. We'll go ahead and share that link in the Zoom chat now. And you are welcome to add questions to the Easy Retro board throughout the webinar. But right before we begin the Q&A portion, we will provide some brief instructions to make sure everyone is on the same page. As I mentioned, we are recording the webinar and we will share this with the registered attendees next week, but we'll also be posting this to our YouTube channel. So without any further delay, Apostol, thank you so much for being here, and we are going to go ahead and pass you the mic.
Thank you, Amanda. Thank you for the warm welcome. I'm excited to be here with you and the audience to talk about AI security. Um, okay, you've made the necessary introduction, so I will not waste much time with it. Let's jump right into it. We all are witnessing the amazing progress that AI technology is making nowadays in a number of different areas of our life. In language, chatbots now a significant part of our network in internet environment. You have personal assistants, translation, summaries. The quality of output generated by AI has grown exponentially better compared to where it was just a couple of years ago. We have advances in healthcare where AI is helping to model protein structure, predict infections, lead to better discovery, and all these things in science. Of course, advances in biology and math. Software code writing, this is one of the main avenues of progress nowadays. Coding assistant, widely used in the industry with varying success. So all of this is amazing progress. But it's important to keep in mind that AI, as useful, as fun as it is, it comes with own risk, and it's important to understand those properly so that we can maximize the benefit and minimize the downside. And that's what I'm going to talk about most of my presentation today, to talk about what are the potential downsides and how they can be mitigated and to what extent. Um, so there's two general categories of risks that come with AI models. One of them, the first one is inherent. These are the errors that models can produce, the hallucinations everybody's talked about. There could be implementation flaw in the model. There could be cybersecurity flaws in the platform on which the model is deployed. And those type of risk, as significant as they are out of scope for this discussion today. They're addressed in other standards. For example, we issued last year a secure software development practices for generative AI and dual use foundation model, which outlines some of these problems and how they can be dealt with effectively. Instead, we're going to focus on adversarial risks, and these are the deliberate actions by motivated adversaries that are aiming to disrupt, evade, compromise, or misuse the operation of the model or its output. So in other words, these are AI inherent or specific adversarial risks that models and can be subjected to. And my presentation will try to give you an overview of what the adversarial landscape looks like. So to help the community with this problem, my team is developing a taxonomy of attacks and mitigations, which is part of the NIST Trustworthy and Responsible AI series. It quickly established itself as a foundational standard in AI security. We try to maintain it annually. The first edition was published in 2023. In March of this year, we released the 2025 version of the taxonomy, which is much, much more updated and improved. Um, in this standard, we are always engaging with the public and seek information on the latest development in adversarial AI, what are the latest attacks, the mitigations, what are the latest trends in AI technologies that promise to transform the industry and society. Just a couple of years ago, we were talking about large language models only. Now everybody is talking about agents, in particular how these models are integrated into the IT infrastructure that we work with in our offices or enterprises. And so this is kind of a new trend right now. The question is what is going to be coming there in the coming year or so. And so if you have some insights with that, please get in touch with us. We really appreciate feedback from the community. As you can see, compared to the previous edition, and now we've extended collaboration on the standard with our colleagues from the UK AI Security Institute. And also, I've invited people from what used to be the US AI Safety Institute, and just this week or last week, the Department of Commerce renamed the US AI Safety Institute to the Center for AI Standards and Innovation. So they are still within NIST and within Department of Commerce, and the new name with the focus on security. So my team is collaborating with them to develop and maintain this document. So what are, very briefly, the new updates, the highlight of the updates? We introduced an index um, in order to facilitate the adoption of the standard and enable fine-grained references to attacks and mitigation. Um, it This index facilitates building compliance checking products by the industry. They want to develop their own tools to automate the process of checking the resilience and robustness of a specific IT infrastructure. Um, this index also will help us position the future development of an API to serve the economy in a machine-readable form, because one of the issues we see from the community of stakeholders is that CISOs in particular are kind of drowning in a sea of AI guidance. And the only way out I can see is through automation. To have automation, you need to have tools. To have tools, you need to have APIs and machine readable form of standards that they can be checked and so on. So we are embarking on a project like that. In the coming year or so, you'll see a different format of the taxonomy. We'll still maintain the human readable PDF form, but we'll go into a machine readable form as well to facilitate automation in compliance checking. And surprisingly for us, we didn't really target that audience, but our index helps develop um, curriculum in higher ed, and we've seen a number of graduate programs in different schools adopt this document as a sort of a background for teaching adversarial AI, which is a very welcomed outcome. We certainly support that. Um, Another important aspect of the update in this version was that we significantly updated the generative AI section of the report with additional classes of attacks. We introduced agents. We tackled the hard problem of supply chain attacks, and I'll talk about all of that in my presentation a little later. And we referenced specific benchmark data sets on adversarial machine learning vulnerabilities that could be useful to assess the suitability of a model that somebody may be looking at in order for their purpose. Okay. So why do we need to actually maintain the standard, the taxonomy on an annual basis? What is happening? And to give you a sense for the pace of development in adversarial machine learning, I'd like to use a graph that shows the number of papers on adversarial machine learning over the course of the last decade. This is somewhat indirect or proxy measure for the pace of development on machine learning. Right now, we don't have developed industry reporting on attacks and mitigations and that sort of thing. So for the time being, we are using this proxy measure, but it's still useful and illustrates very well what is happening. So as you can see, of the course of the last decade, ending in 2020, we have about 3,500 papers published on this topic, adversarial AI on archive.org. This is where preprints in a specific topic are typically published, and machine learning is no exception. And so then fast forward to middle of last year, about a year ago, you see that for the last 3 years from the current decade, we have 3.5 times, basically more than 3 times the number of papers published on this topic, exceeding vastly the whole previous decade. So it's an exponential growth, as you can see. So the question then is, why is this so happening? What is going on there? Is it because this technology is too new and we don't understand it, or are there any fundamental reasons that make this possible? And the answer is actually yes to both. Certainly, this is new technology and there's a lot to learn about it. But more importantly, there is no information theoretic security guarantees for AI algorithm. To give you an example, from another domain, cryptography, we at NIST standardize cryptographic algorithms too. And one of the prerequisites for picking a cryptographic algorithm is to have information theoretic security guarantees for it, meaning that, attackers cannot do anything theoretically to break this algorithm, and people will only worry about the robustness of the practical implementation of the algorithm in software, hardware, or what have you. Worse here in AI, not only are they not information theoretic security guarantees for AI algorithms, but worse, there are information theoretic impossibility results that have been established, meaning that no matter what you do, no matter what you're trying to, or what kind of defenses you throw at it, there are exploits that will still break your system. And I'll touch upon that in the course of the presentation to illustrate. So that makes the security problem really hard to track. And it's illustrated by the graph on the left. As you can see, the number of exploits and defenses really has grown. And unfortunately, the number of exploits far outnumber at the moment the available defenses. So we'll talk about it too. So this is just kind of a preliminary information to give you some context for why we are trying to maintain this taxonomy and what necessitates the frequent updates of what's going on. Um, So I mentioned that this standard is part of the Trustworthy AI standards series that NIST is developing. And just to give you a concept of how we at NIST understand AI trustworthiness, it is defined in terms of 7 attributes. And so if you think of each one of them as ranked between 0 and 10, 0 being the worst and 10 being the best, naturally, you would want all of them to be at 10. And so basically, the idea is that if you have an AI system and it has all of these uh, attributes ranked at a high ranking, let's say 10, then you have a trustworthy AI. The way to think about it is sort of like the famous sort of duck test. If it looks like a duck, if it quacks like a duck, if it swims like a duck, that must be a duck. So if your AI system has these 7 attributes, then it must be a trustworthy AI. And in my talk, I'll focus on security and resilience, and we'll examine that question of how far we can go in terms of guaranteeing secure and resilient AI, and what are the issues associated with that. Okay, so one of the difficulties in achieving truly a trustworthy AI is also the fact that these attributes are not mutually exclusive. In other words, they are dependent on each other, and in practice, it is impossible to simultaneously maximize the performance of the AI system with respect to all of these attributes. There are well-known relationship or trade-offs between accuracy and, for example, adversarial robustness. If you want to make your um, model more adversarially robust, you have to give up on some accuracy. And if you want to make your model extremely accurate or as accurate as possible, it becomes very brittle and easily attackable. So depending on how you want to host this model, whether it's public facing or hosted in a controlled environment, you may want to prioritize one of these aspects at the cost of the other. So basically, organizations need to accept trade-offs and decide priorities depending on the specific AI system, the use case, and so on, in order to figure out a practical way of configuring this trade-off. And there is an example or guidance in the taxonomy that points to the well-known Pareto improvement or Pareto optimization that allows you to consider a practical approach to optimizing the trade-off by hopefully improving the performance on one of the attributes without giving up on the other, or at least not much on the other, in order to optimize the configuration and deployment of your AI system. It's something to think about and have a systematic approach of addressing it if you are considering deploying this technology. Okay, so in terms of the taxonomy, one way we have structured it with respect to 4 dimensions. Um, the first dimension is the learning method and the stage of the learning process. The second dimension is attacker goals and objectives, and we have identified um, 4 major categories of objectives for attackers: availability breakdown, integrity violations, privacy compromise, and misuse. The misuse category is reserved for generative AI systems, not so much for predictive AI systems, and I'll talk about that a little later in the presentation. And the next dimension is attacker capabilities. What kind of control does the attacker have on, for example, the training set, the model, the source code that the model is built from, um, or can do they only have, let's say, normal user query-based access? So all of these capabilities yield different set of exploits or offer different set of possibilities for exploits of your model. And finally, attacker knowledge. How much the attacker does know about your model, the architecture of the model itself, and the architecture in which it is deployed in order to orchestrate a variety of attacks. So all of this are the parameters that define the development of the taxonomy. Let's talk about briefly about the methods and the stages of learning. So there's two main stages that are of interest to adversarial learning. That's the training stage and the deployment. And I'll illustrate that with example as I continue with the presentation. There's two major types of AI technology, generative and predictive. Um, I've discussed this with Amanda and her colleagues, and we're going to focus primarily on the generative AI section. So I'll not talk much about the predictive AI systems other than to say that they are still widely used and highly important in a number of different domains. For example, autonomous driving, the AI models that are used in autonomous driving, they do not generate content. They try to basically figure out the environment in which the vehicle operates and develop or construct a safe path forward. So there's a lot of unsolved, interesting problems there, and we still need to improve significantly the robustness of these systems to make them fully usable and safe. But on the generative side, we are going to focus primarily on LLM and chatbots today, with some examples of agents. That's what organizations are developing and deploying today. So that will be the focus. And of course, if you think about the various learning methods that are used in the industry to develop some of this generative AI technology, they come in different shapes and form. You start with unsupervised learning. There's supervised learning where your data is totally fully labeled. So every data item has a specific label, which allows you to train the model. And semi-supervised learning is um, a combination of the two, where the vast majority of your data is unlabeled, and so is performing unsupervised version training on that part. And of course, a portion of it is labeled correctly, and that's where the supervised portion is. You have reinforcement learning. I'll talk about it a little later. Federated learning is a technique that allows you to spread the learning from a single data set, a single model across multiple of them in order to improve the security of the model so that not a single model knows everything. And that's a useful technique, but not completely foolproof either. And ensemble learning is a technique where you combine the output from several different models in order to decide a common or a single result. And the models used in ensemble modeling may not be the same or the same kind. And that's used in order to introduce some diversity and perhaps more resilience and robustness in arriving at a specific answer. So um, I'll try to give examples as we go forward. Okay. So we talked about attack and knowledge. There is the notion of attack and knowledge falls under the same paradigm as we have it for standard software, namely the black box, the white box, and the gray box. Black box is where the attacker doesn't know anything about the model or the data that is used to train it. A white box is the opposite, where the attacker knows everything about the model, the source code of the model, the data set that was used, and so on. And the gray box is a combination somewhere in between. Um, Black box is typically reserved for the some of the proprietary machine learning model, mostly predictive. But today in the field, we have the transformer architecture used in all of the chatbots that are out there. And of course, on the image generation part, you have the diffusion-based model. So a big aspect of the architecture of every model out there are well known. So they fall into the gray box territory. What is less known is the specific set of data that was used to train each and every one of these models, and that's why we have this notion of gray box. And counterintuitively, uh, for many people who are used to open source in conventional or deterministic software, traditional software, the more you know about the model here, the more exploits you can develop and the more attackable this model is. People think that have assumed for a long time that open source software is more secure because of the so-called thousand eye phenomenon, where everybody's seeing what the code does and how it does it, and they can guarantee or make sure that the code is secure. Of course, this is a very useful and widely accepted practice, but it's not without troubles. We all remember the issues with Heartbleed from a decade ago or so, where an open source system in OpenSSL was compromised badly and led to a very significant problem or breakdown in IT security back then. So, but anyhow, here with the AI systems is actually the opposite. The more you know about the model, the less it is for you to devise attacks that can be mounted on that specific model or could be even transferred to models that are of similar architecture and be applied there, just as a point. Um, just to give you a flavor of kind of to illustrate the taxonomy, a good way to look at it is from the point of view of the attacker goals or objectives. Here, just briefly for the predictive AI taxonomy, which I'm not going to talk about, but just to kind of introduce the visual way of the visualization of it, we've identified the three major objectives for attackers in this field: the availability, the privacy, and the integrity shown at the center of each circle. And then these are the goals. And then the attacker capabilities are shown in the gray outer circles here that illustrate what kind of access the attacker needs in order to mount specific types of attacks. And finally, on the leaf nodes, you have this specific attack category that identifies what kind of attacks the attackers actually do perform in order to reach a specific goal. So this is just a visual of what the taxonomy looks like. But again, we're not going to talk about the predictive AI. Let's turn to generative AI. To talk about generative AI, we'll start with how generative AI models are basically made. What are the stages of learning they go through in order to reach our enterprise or our infrastructure before and be deployed. We start with the pre-training phase, which deals with a huge amount of low quality raw internet data, and that process is extremely computationally intensive. It usually takes, millions of dollars to go through the training of a large language model. The result of it is that you get a base model, which is kind of useful, but kind of rough on the edges. So a lot of work needs to be done in order to improve the performance of the model and align it with human values. So the next stage is supervised fine-tuning, where you take the base model and subject it to training using a small set of low quantity and high quality data that's properly labeled. And then you basically train the model on that data set with the supervised data and produce a slightly better model called SFT, supervised fine-tuned model. which is typically better, more aligned with human values, but still not perfect. Then the next step is to to develop essentially a reward model. The game here is to um, develop reward model that is more or less aligned with human values. And the way it's done is you start with a single prompt, let's say, and you ask the SFT model to generate three or more different um, results for the same prompt. You get three different answers, and you use human contractors typically to score the appropriateness of these answers, and based on that, that gives you a ground truth, and based on that, you developed a reward model that basically is capable of scoring um, outputs or results from the model based on this ground truth classification. This reward model is not really useful and therefore it's not really released, but it's used as in the process the next stage of learning, and that's reinforcement learning with human feedback, where you have human prompts, low quantity, high quality, and the model tries to give you answers that maximize the reward from the model that was developed in the previous step. And that's the result of this process. It's called reinforcement learning from human feedback. And so, as you can see, in this process, I introduced a lot of new artifacts that are required in order to actually develop this model, a bunch of data sets, reward models, and all of that, that affects the final quality of the model. And so, all these data and model artifacts create new risks in terms of data and model poisoning. You can have attacks um, on the supervised fine-tuned model, on the reward modeling, and so on. And in other words, we've created a much larger attack surface to defend in order to guarantee the security and the quality of the models that we worked with. And so most of the models that you see deployed in the fields now and hosted by third-party laboratories are the RLHF models that have gone through all of these stages. Some of the open source models that you see in the field are SFT models. They don't have extensive reward modeling done and reinforcement learning done on them. So they come in different shapes and form, and this gives you an idea of what they go through and the additional artifacts that are required and the potential risks that they expose you to. Okay. So when you get a model like this and you try to adopt it into enterprise, you have to typically uh, first of all, define the problem you want to solve with it. Then you have to choose a model. And you can go for a third-party hosted model, or you can go to and pick an open weights model that somebody made available free to use. Then you go through a process of adaptation and alignment of the model within your business case. You engage with prompt engineering, fine-tuning, aligning with human feedback. All these steps that I mentioned are applied here as well. And finally, once you complete that, you have to integrate the model into the specific workflows that you're interested in automating, and that means further optimization and deployment in the deployment of the model. So roughly, that's the kind of the pipeline that hopefully enterprises go through in order to um, integrate this technology. But of course, from a security perspective, we're talking about additional data sets here and other artifacts that come into play, which further enlarge the attack surface available to attackers. Very briefly, once the model is deployed. Very seldom now we have models that are just used by themselves as just kind of a research tool. Typically, in the case of integrating LLMs to automate specific workflows, in the enterprise, you have an orchestration library that allows users to interact with the model and connect it to specific data sources that are available to the model to perform RAG or retrieval augmented generation to make it adaptable to the specific domain of knowledge that your organization is working on. Um, they could be internal documents, databases, or even some external web references. And of course, LLMs often rely on external applications to complete some of their responses. For example, they have sometimes trouble calculating complicated arithmetic expressions or doing algebra and that sort of thing. And people often offload these operations to specific libraries and tools that can do that. And once the calculation is done there, they return it back through the orchestration library to the model to respond to the specific queries. And of course, LLMs can operate on email systems and generate the email or even trigger API calls to um, exercise specific support actions or trigger a service request and things like this. So we are now talking about not just LLMs, but we're reaching into the agentic world of how LLMs are being deployed, and I'll talk about it some more further down. Anyway, so that's an illustration for high-level architecture, how things look when the technology is deployed in the enterprise. And of course, by itself, this architecture offers new opportunities for attackers to reach out to LLM and exploit all of this data and infrastructure that's available to them through prompt injection, jailbreaking, and other techniques that I'll talk about as well. Okay, here is a flavor of the Gen AI taxonomy. It's very much the same as the one I showed for predictive AI models, but here we have introduced on the right side the misuse category, which I mentioned early on. And it's basically about ways, it is specific to the generative AI technology. And of course, it is attacked using the same kind of techniques, just different goals. And I'll talk about those a little more in context. Okay. Um, so let's talk about integrity violations as the first class of attacks. The, the objective here is to cause generative AI system to become untrustworthy. And so there's two types of attack during training and during inference. I mentioned that these are the two stages of learning that are of interest to adversarial AI, and here it is as well. So in training time, poisoning attacks. These are attacks that essentially modify data sets that are used to train the models with the intent of affecting the performance of the model or the behavior of the model downstream negatively. And so the question is then how feasible is that? How much data do you need to actually alter in order to achieve the desired objective? And it turns out that a small fraction of percent is actually needed in order to achieve that, which makes large-scale poisoning feasible. And model fine-tuning, obviously, we illustrated that it requires many additional data sets, and this is really an area which could be poisoned or attack surface that can be exploited and poisoned by attackers. So that another area of concern. And another interesting aspect of open weight models is they open the door to model poisoning attack. And there is an interesting paper that came out in 2024 about sleeper agents that attackers, researchers developed capability based on an open model, trained it to do some nefarious things, and that training persisted over several subsequent alignment rounds. And so I'll talk in some details a little later about these specific attacks, but just so you know that not only data sets can be poisoned, but models as well during their fine-tuning stages. And of course, there's the inference time attacks. You have your model, you've deployed it. So what can attackers do to them? And one example is that they can instruct the model to give the wrong answers. In the context for that is indirect prompt injection, where the model may reach out, as I illustrated, to the web in order to complete some of the requests that they received from users, but ingesting web data in context of responding to a prompt is problematic because the web data may come with additional instructions to the model to do things that the user is not suspecting of doing. And that's where you enter the territory of indirect prompt injection. So, what can you do to mitigate some of these risks? There is no single silver bullet that you can rely on in order to defend against this thing. Security in this case is best addressed comprehensively, including looking after all the software, the infrastructure that you have, the data sets, and the model supply chains, network and storage systems. One good practice of hygiene is to apply news provenance and integrity checks for datasets and models. For example, cryptographic hashes, PKI certificates when it's possible, and things like this. And of course, a good practice is also to sanitize your data, to inspect it, to see if the data sample that you're using to train your model does not have some out of distribution samples that indicate poisoning or attacks. So there's tools that allow you to do that, but there are also theoretical limits of how robust this technology is to detect out of this distribution data. It turns out that in the context of machine learning, there are some theoretical limits, which I alluded to in the beginning, about how reliably you can detect and filter out of distribution data. It turns out that when you have distributions that overlap, you cannot sort them apart. And that gives, it's a well-known theoretical result that has been known in physics and other areas for quite some time. But a couple of years ago, researchers have proved it in the context of machine learning. And so because of it, attackers have an opening essentially to construct their adversarial examples in distributions that are overlapping with the natural distribution where a model is trained, and that gives them an opportunity to attack. So tools are useful and needed because these data sets are huge and you cannot afford to inspect them by hand, but with a naked eye. But you need to be aware of the limitations, and you still have to monitor and ensure that your model is performing well. Okay. Availability breakdown. Well, these are threats that cause a disruption in service with maliciously crafted inputs that lead to um, some kind of denial of service. That could be simply because the system is overwhelmed by giving it time-consuming background tasks that cause it to compute um, significantly larger amounts and therefore becomes unavailable to other users. Or attackers can submit specific tokens to cause the models to not complete the sentence or mangle the output text in ways that make it unusable in downstream applications, or the attacker can instruct the model if it is in the context of an infrastructure that has access to specific APIs and tools and things like this. The attacker may instruct it to avoid specific APIs and cause disruption of service that way. And I also mentioned here using homoglyphs in order to cause disruption of services. What is a homoglyph? Well, it's basically a replacement of a letter with a digit. For example, you replace O with 0, or I with 1, and that sort of thing, just to mangle the output and make it problematic for downstream services that you have configured. So, so these are some of the examples of attacks that exist against models. Um, what can you do to defend against those? Well, the best you could do is to monitor and be prepared to act when a breach is detected. And the NIST AI risk management framework is a good source for how to do that and establish the robust governance structure in the enterprise so we can do it consistently and robustly. A good practice here is to obviously inspect and filter user output to the extent possible. Just recently, a new development in this aspect was the camel defense that was introduced just earlier this year. The idea is simple. Make sure that when you're inspecting user input, you discriminate control flow from data, kind of what people use in SQL injection in order to detect protect against SQL injection attacks. And that way you can impose security policy on the control side of the input of the prompt, and therefore eliminate a whole host of potential exploits. This is good. To implement this defense, you need a specific layer that you put in front of the LLM in order to filter the output. So it's not just within the LLM, but you use a layer, protective layer, a filter in front of it. It's a useful technique. But of course, it is not perfect. It doesn't prevent everything. It just prevents uh, significant part of potential attacks. So it is something to consider if you are deploying the AI technology. And I mentioned already, you have to monitor the runtime state of the system to detect a breach, and you have to have a plan for recovery from a breach, because organizations that are prepared have lower losses than unprepared organizations who are just trying to improvise when a breach happens. And typically this leads to longer times of recovery and more damage. Okay. So prompt injection. Prompt injection is probably the most well-known type of attack against AI models. The idea is that the attacker can't control the LLM prompt and can modify or replace parts of it in order to cause answers that fit the attacker's purpose, but not what the user wanted to get out of it. And it's illustrated here where attacker can essentially tell the system to ignore everything else and just print something silly. And this is one example of a direct prompt injection. And of course, indirect prompt injection is when the attacker is trying to indirectly manipulate the prompt when um, through a web resource, external web resource. So basically what they do is put hidden um, instruction within the source of the web page that the model is going to access, and that becomes an instruction for the model when they essentially respond to the prompt, and can cause all kinds of um, unintended outputs. Okay. Misuse violations. I talked about that's the next class. I talked about this class as specific to generative AI technology. The idea here is that the attacker tries to repurpose the system's intended use to achieve their own objectives by deliberately circumventing technical restrictions that are imposed on the system. Um, and generally, these are not model features, but harms that manifest themselves in the context of model use. In other words, it's not so much of a problem that the model can generate specific content, but how this content is used downstream is where the problems arise. And so you can have inference attacks based on indirect prompt injection in order to commit fraud. Um, you can create a very convincing phishing scams attack. You can cause the model to pretend to be an official request from a service provider and to recommend fraudulent websites for users to access. You can obviously create deep fakes to defraud others. Um, Generative AI models are used for malware generation. They can generate not only code, but they can generate bad code or malware in order to facilitate spreading of the injections or malware in general. So they can also misuse violations manifest themselves as manipulation, where the model can be made to introduce historical distortions. For example, instead of reporting well-known information, they can be coerced into uh, producing disinformation. For example, they can deny that Einstein won a Nobel Prize, just as a simple example, or they can steer the generation of results towards a specific orientation in order to cause um, bias in a specific way, whether it's liberal or conservative or you name it. There's examples of that sort of attack. So just to illustrate, jailbreak and prompt injection are two different things, and some people confuse them. Prompt injection means that you can replace and manipulate the prompt of the user, but that doesn't mean that the model necessarily will do something that breaks the technical measures that the developer has put in order to prevent specific type of content to be generated. And jailbreaking does exactly that. It aims to break the guardrails that are put in place in order to produce problematic content, as it is illustrated in this example, where a model is being asked to provide instructions for how to destroy the humanity, for example, and the model is often deceived or to and caused to produce this sort of result. Not a good outcome, but it's something that attackers can do. Um, Going back to the poisoning of models during fine-tuning. Okay, I talked about using open source models to make them generate code, insecure code, and then that's the sleeper agents paper that I referenced, and then following this poisoning, the researchers then performed several rounds of alignment to see if the poisoning will persist, and it did. Essentially, what it means is that you can train the model and then to generate insecure code, And then you can tell it to go back to generating secure code and deploy it that way. And when the organization that's using it least expect, then turn on again the insecure code generation mode in order to cause trouble within the products that this organization may be developing for internal use or for third-party clients. And that's essentially is a stealthy attack, multi-step attack that is shown to be possible on models like that, and it works particularly well against open weight models like what you have now in the field. Okay, so talking about models and open models, the risks associated with them, we need to consider briefly the corresponding supply chain challenges. Very few organizations are capable today of developing their own models. So most of the organizations really get a model from somebody else, whether it's an open weight model or a third-party hosted model. Talking about model weights and their importance for the behavior of the model. We're dealing with models that are extremely large, in the billions and trillions of parameters. And that means that there's no way one can make sense of what the specific model weight configuration means for the behavior of the model. Just to give you an example, if you look at them, they're just arrays of a large number. Looking at them, it gives you no hint as to what the model can do. What are the behaviors that's encoded into this set of numbers? Which means that if you're getting a an open weight model and that comes with specific weights, you better know who's done what to your model, because just looking at the model binary and the model weights, you're not going to be able to tell what this model does. And that makes the supply chain problem a little more complicated than that for traditional software, where you can have checklists. You can even look at the source code or the binary and understand the behavior of this piece of software. Not so in this particular case. And that's why people say that the current AI technology is fundamentally different than conventional software. Talking about data set and supply chain issues associated with them, we've talked about several times already about the need to make sure that your data is secure, that there's no poisoning, and so on. But when you're dealing with large data sets that come from various web sources, um, people need to realize that large models require large training corpus, but large data sets are not monolith data blocks on the internet. There is no single server that contains a single instance of this data. The data is spread all over the internet, and a data source on the internet is simply a pointer to many other web sources which contain the actual data samples. And that creates a very difficult to track security problems, and it can be easily exploited. Okay, so very briefly about potential misuse of mitigations of misuse violation. Well, reinforcement learning, applying more rounds of alignment is a way to do that. We still have to filter the received inputs to the extent possible. That's the camel defense that I used. And another approach is to use LLM moderator to detect attacks beyond filtering the harmful outputs. And of course, interpretability-based approaches where you try to detect outliers in your output generation in order to detect deviation from standard distribution and stuff like this in order to detect this sort of exploits. People have tried to implement ideas of certifiable robustness by introducing semantic distance in order to be able to filter out outputs that are ineligible, with the idea that if you have a bad input um, prompt, everything that has is in a close semantic distance away from this prompt, you reject, and everything works out fine. The problem is that there are two issues here. One is the so-called impossibility results that were introduced in 2023 by Glukhoff and company, as well as Wolf and company as well. What these people showed is that there's fundamental theoretical impossibilities to um, uh, basically censor user input and reject specific kinds of input. It comes down to finite systems of rules that you use in order to develop certain controls over the input. It comes down to, in the end, to the famous Gödel theorem of incompleteness. If you have a system of axioms and you build a theory on top of it, there will be statements in your theory that you cannot decide whether they're true or false with respect to the initial axioms. So you have to put new axioms in it to fix that. But if you do that, there'll be other statements that you cannot resolve. So that it's kind of the gist of the arguments that these people have made. And of course, practically the problem of semantic distance was illustrated by a counterexample that was demonstrated by the so-called ASCII art attack, when a model was asked to give instructions for how to build a bomb with a simple prompt. It refused. But if you entered the same prompt by introducing ASCII art, where the word bomb is introduced as an ASCII art, and you give the model instructions for how to decode the ASCII art, then the model is happy to give you that sort of instruction. But it tells you that in one case you succeeded, in one case you failed. But why is this a problem with respect to semantic difference? Well, the semantic difference between these two statements is exactly zero. So if you were to filter out all these statements that are close to how to build a bomb, then you should have filtered that one, except that it didn't. And so, this tells you that there's a lot of uncertainty still here, a lot of work to be done to see what's feasible in terms of providing some security guarantees for this sort of technology. So what can we do in the face of impossibility results? Well, these are for sure discouraging results, but there are certainly measures the organization should take to get some protection, with the understanding that this is not going to be full immunity. The one thing about the impossibility results that I mentioned is that they're based on indirect or non-constructive math proofs, which means that an object, a mathematical object, exists without providing a specific example of how to construct it, or basically it's a proof by contradiction. So that means that attackers have no recipe for constructing the attack. They have to still engage in a long, exhaustive process of trial and error. And on the flip side, defenders have no metrics for testing the assurance. So you can't determine how much red teaming is enough for you to feel safe. So the best possible defense in this context is to use essentially a cycle of red teaming your system and making sure that you have, based on making sure that it's resilient against all well-known attacks or known attacks, and you make the target moving, so it makes it harder for attackers to actually exploit it, makes it harder for them to find a new way to exploit it. But anyhow, it is a cat and mouse game in the context of lacking theoretical guarantees. Other useful defensive approaches is to use a panel of LLM judges to monitor and decide the alignment of the output produced by a model to see whether it's accepted quality and accuracy and so on. And you can use these techniques. They are computationally intensive, resource intensive, but that's at the moment the best you could do to improve your security posture. Okay, very briefly, privacy compromise that are threats that exposed to extract sensitive information about the user or the model, and it have in inference time attack, we have data extraction, or you have indirect prompt injection attacks that are designed to elicit or extract um, uh, privacy information. Examples of that have been shown in the literature. Um, Existing methods, again, nothing foolproof. Um, you have to train for alignment. You have to monitor the prompts, and you have to make sure that you filter out to the extent possible ineligible prompts. Very briefly about agents. Agents are essentially LLMs wrapped with additional infrastructure in order to enable their function and the ability to automate specific workflows and stuff like this. I already illustrated that early on with the general diagram. Um, Agents introduce new risks because they take actions using tools and therefore enable actors to hijack agents to execute arbitrary code or exfiltrate data from the environment in which they're operating. The security of agents is still in early stages, the research about it. I'm collaborating with the OWASP community, their Gen AI security project to develop guidance about that. Earlier this year, they released Agentic AI threats and mitigations document, which is useful. Just um, yesterday, they kicked off a project to develop a system for vulnerability scoring system. And so that means that you'll be able to hopefully quantify the risks associated with specific types of attacks. And that gives you a handle of actually performing more robust um, or effective risk management within your enterprise, and hopefully it will give you a better way of understanding the risks that you're encountering and ways to mitigate those. Okay, let me finish here with a couple of notes on some of the open problems. While we still need to understand fully the vulnerabilities in modern AI systems, we talked about several of them. We talked about some impossibility results. The question is, what other exploits are available? Are there any robust mitigations that can be introduced? I talked about the trade-off between the various trustworthy attributes for AI models and the question of trade-offs. A lot of research is needed to understand how these trade-offs work and whether or not it's possible to alleviate some of the trade-offs between accuracy, robustness, and other attributes. And then, of course, looking at the entire life cycle, can we provide um, strong guarantees for AI, for the AI technology within the context of the entire life cycle? AI privacy, in particular, what other privacy risks associated with the different threat models in AI? And can we actually scale up differential privacy and privacy auditing to larger models in order to obtain some more consistent or systematic guarantees? See, these are some of the open theoretical problems that exist for the community of researchers. So to end it here, AI friend oh 04? Well, it depends on how you flow. With that, I'm open to questions. Thank you.
Excellent. Thank you so much. That was so fantastic. Folks, We are sure that you have some questions kind of floating around in the space. I know this might have been a lot of new information for people. I noticed on the Easy Retro board that we dropped into the chat, a couple of folks have added items. So I just want to take a minute to walk you through the retro board itself to make sure we know how to add questions. So feel free to scan the QR code on the screen or use the link that we have provided in the chat. And quite simply, you are going to click on the plus sign in the relevant column. And Jess, if you want to go ahead and uh, show the Easy Retro board now, that would be great. Thank you so much. So, yeah, so to go ahead and add ideas, just click on the plus sign in the relevant column and type your idea. And when you're finished, hit the blue box with a thin white check mark and save within the same field, and your idea will appear on the screen um, for the public's reaction. And you can also comment on other attendees' ideas and questions. You can upvote someone else's idea using the thumbs up icon and comment on an idea using the quote bubble icon. So, with that in mind, I'm just going to walk us through sort of left to right here, Apostol, if that's okay.
Yeah.
Super. So, because organizations will continue to develop new and better frontier models, and because there is a lot of money sloshing around AI development, are any standards organizations or other government entities considering assembly of a sanitized data set for the training of these models? I heard that the Utah data facility was epically large. Could such a facility serve this training data securely?
That's a good question, and certainly seems like a good idea to think about. I'm not aware of a specific plans that the government has around the Utah data sets, and in addition to that, the frontier labs keep very close to their chest the specific data sets that they use in order to claim competitive advantage over their competitors. So, I understand the question. I see the value of it. I don't know of any specific plans that are there to make it happen, and I don't know if the frontier labs um, are going to be happy with that data set alone. They're always going to use additional data sets. And so it's the cumulative effect that gives you the total risk exposure. It's not just one particular data set.
Okay, thank you. Yeah, and I'm just looking now at the miscellaneous column. Are there resources from NIST that organizations can start referencing for guidelines for creating robust AI models?
Yeah, there are. I mean, we are developing those resources. There is the NIST AI risk management framework, which is a starting point in for any organization, whether they're developing or deploying the technology. And then we have guidance for developers of AI models or organizations who are integrating um, models into their infrastructure, secure software development framework for that. There's guidance associated with that. We maintain AI a resource center. There's a lot of useful guidance there. I would recommend people check it out and study it in order to get a starter on this point. We have a number of projects in the pipeline at the moment. We are contemplating essentially uh, connecting or mapping the taxonomy that I talked about today with the SP 853 uh, cybersecurity controls that have been quite popular in the IT community. and making essentially a very kind of detailed and instructive set of guidance, uh, saying, okay, directing people for how to approach the security of AI models in the context of the infrastructure that they develop. So there's a lot of guidance and there's a lot of emerging guidance, and um, we'll be announcing events, and we'll solicit participation from the public to come and help us jointly develop this guidance.
Fantastic. And so that kind of leads into this question, also in the miscellaneous column, but are there efforts to disseminate the risks and potential remediation beyond academia? How about governance policy around these issues? And from what I've seen, there are a lot of great resources available, as you mentioned, in the AI risk management framework that NIST has online. And I dropped a link to that in the chat for folks to reference. But anything else to add there?
Yeah, absolutely. I mean, the OWASP community at the moment is extremely active organization developing AI and specifically agent guidance. I mentioned the initiative to develop this AI vulnerability scoring system. And so these are developments that are noteworthy in AI security and can benefit all of the stakeholders in AI. So I encourage you to look for those resources on the web and engage with those communities to participate and tailor the development of standards to your needs to the extent possible.
That's great. Thank you. Um, so I'm going to now jump over to the top question in security of Gen AI models. How much are these risks affecting businesses that use generative AI more sparingly, like ChatGPT, such as for a code generator or editor, as opposed to organizations that are training their own models?
That's an interesting question, and there is no really an easy answer to that question. But I will say that closed models and open weight models do offer different attack possibilities, and um, you may think that, on one hand, yeah, you are protected from, let's say, model poisoning attacks because a frontier lab will have a lot at stake in order to serve you something nefarious and all that. But when you are working with them, you have other issues. For example, leakage of proprietary information and things like that. So it's a trade-off that every organization needs to make for themselves. There is no one rule fits all kind of situation, and people have to assess the problem locally.
Okay. So in that same column, I'm just going to read this comment slash question. I tend to believe that AI-driven cognitive hacking will become a significant emerging threat. Given that cognitive hacking exploits AI model poisoning to manipulate outputs and influence decision making, what technical measures do you recommend to protect AI systems from these attacks? So that's the first question. Considering that attackers can gather personality trait information not only from external sources, but also from the data used in model training, which protection measures do you believe could serve as effective defenses against such attacks? And then there's the question of LLM-based moderator as adaptive monitoring.
Yeah, these are good questions. They're difficult to handle as well. But the thing is, cognitive hacking is essentially a form of misuse. And the mitigation techniques that I kind of briefly introduced there could be employed. One of them was to, for example, use this panel of judges, of LLM judges. Essentially, you have one or more models whose job is only to assess the output from the primary model that you use to service user requests or prompts. And so you can employ some kind of a voting scheme among the judges to decide whether an output is acceptable or not. And that's, you could use a consensus or a majority vote, that sort of thing, to decide how to judge a specific output. And that is a technique that people have used and proposed in the field. I have references in the presentation to some of these architectures that allow you to essentially mitigate some of the risks associated with cognitive hacking or misuse, let's put it this way. Um, they're not perfect, they're subject to specific exploits, or they cannot filter out everything, but they certainly raise the bar and make it harder to exploit the system, the original model with that. Um,
Okay.
what was the other half?
It's up here on the screen. So, considering that attackers can gather personality trait information not only from external sources, but also from the data used in model training, which protection measures do you believe could serve as effective defenses against such attacks?
Well, it has to be a comprehensive approach. You have to, first of all, ensure that your data is sanitized. That goes um, into the training of the model. But then you have to monitor the runtime state of the model, inspect the user prompts to make sure that they don't throw something inappropriate. You have to filter to the extent possible the web inputs that you're getting through, let's say, indirect web sources in a RAG scenario, the retrieval augmentation generation. So it's a comprehensive set of measures that you have to take. There isn't a single silver bullet that is going to say, okay, you do this and you're safe from now on.
Okay, thank you. So I'm going to look at this next question in that column. Is there a possibility of deployment time attacks for businesses who integrate third-party AI into their platforms?
Yeah, absolutely. These models, based on the same architecture, and whether they're open source or open weight models or closed models, they're subject to the same attacks. They're subject to the same impossibility results that I referenced. And so, yeah, and you basically have to worry about all of these things, whether you're using closed models hosted by a third party or your own on-premise hosted, open weight model.
All right, great. And then I'm going to just take our final question here. This is also from the miscellaneous column, but a different take on trustworthy. I have found Claude and ChatGPT to be far too sycophantic and eager to affirm the premise of my prompt or stroke my ego. When I have pressed for a reference about a point the AI emphasized, both systems were evasive until I pressed again and again, and they ultimately admitted they made a false claim. What is the outlook or possibility for AI to become more intellectually rigorous?
Well, great question. The thing is, these systems don't have the ability to reason the way you and I do. I think it's an illustration of the classical gap between cognitive intelligence and the automation of a cognitive tasks. These systems generate a statistically plausible response um, based on a user prompt. That's it. They don't really think in the context of the information that is given to them the way people do. And so, therefore, this is the reason why hallucinations are so elusive and impossible to fix within the existing technology paradigm. And so, what you are seeing is a system that is trying to give you a result that is statistically plausible to your prompt, but that's the extent of it. That's why they don't know how to provide references, legitimate references to support their claims, and so on. So you're not interacting with a living intellect. You're interacting with a statistical system that is trying to give you a statistically plausible answer.
Right. Oh, okay. So, okay, I said that was gonna be the last question. We've had a couple more pop up in this left column. Um, let's let this final question here be the last one. I have been reading recently that frontier model developers do not fully understand how their models produce the outputs that they do. Is NIST performing research in this area? And that is going to be our final question, folks.
Yeah, that is true. There was a famous blog post by Dario Amodei. He is the CEO of Anthropic, one of the leading or frontier labs. And basically, he said, yeah, the two things. One is that this software, AI software, is fundamentally different than um, conventional software, and they have no clue how these things work. Um, Literally, pretty much, I'm almost verbatim. And so, yeah, this is a well-known problem. People are doing research on everywhere in academia, industry, try to get to the bottom of it. NIST is not specifically researching in this area. We are essentially trying to stay on top of the existing research and trying to inform the community about what's coming and what's next. But we're not directly involved, to my knowledge, in that research.
Okay. All right. Well, thank you so much for your time today. Thank you for the amazing work that you've shared with us. Are your slides going to be made available?
Sure, I can send them to you.
Yeah, that would be great. That would be great, folks. We will be happy to include Apostol's slides when we send out the recording. So thank you once again for your time and energy today. This has been an amazing session. Really looking forward to feedback from everyone on how things went. We might be asking you for a round two because there were plenty of questions, and I know that there were some we didn't even get a chance to get to today. So thanks, folks, for joining us. This was our final event for this fiscal year. We'll be back in the swing of things starting in August and looking forward to sharing our fall lineup with you in our newsletter next month. Do take a minute to complete our evaluation for today. But Apostol, thank you so much for your time. This was incredible. Really appreciate your research and making this information available. Thank you so much.
Thank you, Amanda. It was a pleasure, and looking forward to more in the future if possible.
Super. All right. Thanks so much, everyone. Take care. Bye-bye.